So we're going to look at some problems on the rotating Earth. And we're just going to begin by talking about the rotating frame on the Earth and how it's sort of laid out. And so this is a picture of the Earth as viewed sort of from the side. Here's the rotation axis. It's rotating at angular velocity omega. And I wrote down the angular velocity omega is 1 revolution per day. That comes out to, we did this in basic physics, general physics 1, 7.27 times 10 to the minus 5th radians per second. If you divide 2 pi radians by 86,400 seconds. And so when we're solving these problems, we'll usually have a rotating frame that's attached to some point on the Earth. It may be in your town or in your lab or something like that. And so the z prime axis is perpendicular to the Earth. The y prime axis kind of points north because this is the North Pole up here. The x prime axis points into the board. And so k hat is local vertical, j hat is north, and I hat is points east. That angle lambda is your latitude angle. In Oklahoma, that's about 35 degrees, something like that. Rho is your distance in wherever you are from the rotational axis. It's just rho is equal to the radius of the Earth times cosine of lambda, wherever you are. That's your sort of your distance from the rotational axis. And the first thing we notice is that the origin of the rotating frame gives 0 for all the terms in our acceleration that we've sort of named. Right, this is our acceleration is viewed from an inertial frame. This is for our acceleration from inside the rotating frame, and these are all the terms that result from the coordinate system transformation. And so omega cross r prime is the transverse acceleration, but r prime is 0 at the origin, and so the origin gives 0 for this term. Similarly, v is the velocity in the prime frame. In the prime frame, the origin is motionless, so we get a 0 here. And again, r prime is 0, and so we get a 0 here. And of course, a is 0. A prime, sorry, is 0 in the rotating frame because it's the origin. By definition, the origin isn't moving in the rotating frame, and so all these terms are 0. And so, but we do have an accelerating frame here because the frame itself is moving around in a circle rather than just having the same origin as the rotating frame. As the inertial frame. The rotating frame is now set out at a distance, and so it's moving around the origin of the stationary frame, and so we have to take that into account. So if I acknowledge that the frame is being accelerated, then the acceleration in the inertial frame is equal to the acceleration in the rotating frame plus all of these terms, which we just showed are all 0, plus the acceleration of that frame because it's going around in a circle around the center of the around the rotational axis of the Earth at radius rho that we did in the last problem. And so since all of these terms are 0, if I'm sitting at rest at the origin of the prime frame, my acceleration is just a0. And so a0, the magnitude of a0 is just omega squared times rho, and that's equal to omega squared times the radius of the Earth times the cosine of lambda. And so on the next in the next activity, we're gonna look at what is the deflection angle of a hanging weight, and I'll explain that in the next video.